Great. So for our next talk and for the we'll have Adam, Tom, and Kalai talking about some, I think, very recent work on loss minimization and multi-calibration in large neural networks.
Thank you. Thank you for inviting me. This is joint work with these great co-authors. Udi would have been a co-author, but since he left, we've decided to remove him. So his talk was light. This will be extra light and conceptual. And I'd love to have questions during the talk, so feel free to ask. Let me just start with the boosting, because as you all know, multi-calibration is related to boosting, and it's boosting is kind of like the predecessor, or the easy version. And there's some classifiers. If you're learning half spaces, you can definitely get a better classifier by boosting them, obviously, or as many people know. Here's an example where there's no good half space for learning this, but if you were to boost half spaces, you would probably learn this perfectly to separate the positives and negatives. But you don't really see as much work on, say, boosting large neural networks. And, well, that would be expensive because you'd need many of the neural networks, of course. There's another reason we say, which is that, like, what does boosting do? One of the simplest forms of boosting, Shapiri's original version of boosting, was it just took the majority of 3 classifiers. You train one classifier on your data, then you train the second classifier on a mix of the correct and incorrect examples equally weighted, and a third classifier where those two disagreed. And you took the majority of these, and that worked great. And there's a lot of boosting algorithms that work by just taking the majority of classifiers. It's good enough. And the majority function is, you can write it as a neural network too. So instead of training a neural network in this way of training several neural networks in specific ways and taking the majority, you could just train a larger neural network. And if you could optimize perfectly over all neural networks, this should do only better. Right? Does that make sense? So optimizing a large neural network should beat boosting small neural networks. Especially if you could find global optimums. There is something you can say in the case where you can't that I'll mention later, if we have time. So just formally, if you had the family of neural networks of size at most S nodes, and you can, it's not very important, but there's some details of what the activations are in the neural network, then the most accurate neural network with N nodes is as accurate as boosting if you have a number of iterations times the size of the smaller neural network, basically. Okay, that's exactly what I said here. So that's kind of the warm up. And the fact is that I claim I checked with GPT-4 this morning, so that you don't see that much boosting with neural networks. And so GPT-4 said in general, boosting is not commonly used together with deep neural networks, and it has a long explanation. Which I was satisfied with because it confirmed what I wanted. GPT 3.5 disagreed, but it wasn't as good as this GPT-4. Okay, so the outline is, we talked about boosting neural networks, and now I want to talk about it with respect to a similar thing with respect to multi-calibration, which will be slightly more complicated, but the same idea. And then I'll talk about some related work, and this is where it'll get fun, is the conceptual discussion is like, what does this mean? What do we take away from this? So the claim is that large neural networks don't necessarily need multi-calibration, and similar to the boosting. So well, let's say we're in a binary classification setting or regression setting, and we're trying to learn some function from X to Y, and we're minimizing squared error. So then we want to, now I wasn't here yesterday, and I'm sure there were like a gazillion forms of multi-calibration presented, I hope. So I hope this was one of them. But I don't really want to go into the definition of multi-calibration, the specific definition of multi-calibration we have. What's interesting here is we say we're going to have a notion of alpha multi-calibration for some parameter alpha between 0 and 1. And what we would like to say is that, if we could perfectly minimize over neural networks of size n, then we would be multi-calibrated with respect to smaller neural networks, so that the tests themselves will also be neural networks, but they'll be smaller. And we'd like to get that, but it's not quite true for all neural network sizes for a reason that I'll explain in a second. But it is true for many neural network sizes. Okay, there's some number of neural network sizes which might not be true for, but all a finite number of them. And so depending on this parameter alpha and the size of the small test neural networks S, it'll be true beyond that. So basically, if you want to get something multi-calibrated, it would be good enough to choose a neural network size that's pretty big. If you want to be multi-calibrated with respect to set neural networks of size S, and you choose a random one in some range that's much bigger than this range, then with high probability it'll be multi-calibrated.
I'm wondering about the sort of like careful statements of the theorem. So do you not know that some size that's of that is sufficient? And I just that size.
Do we not know what? Say it again.
You're saying for at most this many integers. Like it almost sounds like there could be some like arbitrarily
some huge one like randomly.
Yeah.
The next slide, which has a proof, will shed light on exactly what's going on. But it could be, as far as our analysis goes, that the bad ones are like far out. But you can actually check and see whether you're multi-calibrated or not. If you could actually efficiently minimize perfectly.
Say you're talking about the size of the network, but you're talking about particular architecture. This is
our architectures, our architecture is a very boring, simple one where it's just a DAG. It's just like any DAG architecture, and then the nodes could be connected arbitrarily to the lower ones, and we're counting the number of nodes.
I mean, maybe for S, but clearly that's not the case for N. You could think of N should just be a chain, a long.
It could be. I'm saying we're optimizing over all neural networks with S nodes over any DAG.
Instead of all networks, I see. So you're not fixing the architecture.
No. It would be interesting. We didn't really look into it to consider how the relationship between the large architecture and the small architecture. We just did this for simplicity.
So wonderful. But how does it correspond to the results Michael and others had where neural networks failing, then calibrate them, and then try the gender shape, for example, where neural networks is horribly
right.
And with a little bit of person confused too much.
Yes. Was
Michael also
I can ask the expert here.
I think they trained with different data they use different data to do the adjustment.
Yeah. So generally the problem with gender shape is that my impression was that it was a lack of data, which is what you're saying, like there wasn't enough training data from minority groups. But also when you know which group you care about, sometimes you can also focus your loss more there. Like multi-calibration weights the groups based on their representation in the data, right? Effectively.
Right, and also to the point about what we're optimizing over here, you're saying like, it's not saying that SGD on the fixed architecture is going to find this optimal. It's saying that there exists an optimal neural network, sufficiently large size.
But I have something to say about SGD too. But I think that
That's sort of an ignorant question. When you train neural nets in general, are they even globally calibrated?
Typically you're asking, or like, I mean, for example, the GPT-4 paper that recently came out showed a beautiful calibration curve on its weights, but that's just one example. And I'm sure there's exceptions. There probably are cases. There might be cases. I'm following the general trend is not to boost neural networks or to apply multi-calibration. Maybe there are exceptions, and it would be super interesting to look into why that's happening.
There is a non-linearity. It's just not interesting, or you didn't really mention it.
The ReLU?
Did you say ReLUs? I just
yes.
Thank you.
Great questions. I love it. So, and the proof, which is very simple, is the basic idea is we say, look, suppose you're not multi-calibrated. Suppose there's some test C, which is a small neural network, which demonstrates that your best neural network of size n, f, n star, but let's just say we could exactly minimize loss for a second. Suppose that that was the case, then there exists some better neural network which kind of combines these two with some simple logic there and some weights. it only takes like 3 nodes. I'm not going to show you what it is, but it's not complicated. That larger neural network, which is the size of n plus c plus 3, will have error loss, squared error alpha squared lower than yours. Okay. I think this is implicit probably in various works. So we're just, an interpretation of that is saying, oh, look, so now, okay, this is kind of interesting. So first of all, this function, you could just look at the loss of the network, the best network of size n for every n. And if your network loss is not much bigger than what you get if you take a larger network. So if there's not too big a drop, if you look at the drop in the loss, then this answers the question, your question from before. So you're in good shape if you compare your loss to the best loss with a slightly larger network, and there's not a huge drop. If the drop isn't bigger than alpha squared, then you know that you're multi-calibrated, alpha multi-calibrated with respect to the smaller networks. So whatever this loss function looks like, it's decrease. It's definitely not increasing because it's the best neural network of size n. So there could be at most 1 over alpha squared drops of magnitude alpha squared. Let's say if you just check neural networks of size multiples of s plus 3, and then you could do this for every mod s plus 3 for each one, and then you get the statement that there's at most, this is the number of bad networks, but also you get the statement that this is like a way to test and confirm. But they could be, it could weirdly be that the loss goes out here and then drops weirdly at some random size that you happen to pick exactly. The sizes that people use are billions or hundreds of billions or trillions of nodes. So it's unlikely that you would hit on that one, but it's possible. We actually have another way, but you could do this test. You could train 2 network sizes to see whether you're actually at that weird point. Or you can also use regularization to get around this and choose a neural network size that minimizes some combination of loss and size. So, okay. So let me just mention a couple other related works, but if there are any questions on this, or that discussion is very important about the interpretation. So my sense, but that's where it would be great to have the expertise of the audience here, is that that you may not need empirically. I'm not aware of a ton of work which combines it. So my sense is that if you have a weak classifier, like a half space, weak in some sense, it's not, it doesn't compose with itself, right? If you, it's not closed under composition, then you're going to get magic by multi-calibration, and you can actually, you get these branching programs. Of course, those are basically networks too, kind of like neural networks, it's all circuits. So you've got another way to generate a large network with some provable guarantees, maybe not as good in practice, or it doesn't seem to be as popular in practice, but you get the theory guarantees. Whereas if what your base classifier is neural networks, not clear, you need this.
So you're searching over not just parameters, but also the organizer?
In this, yeah. So, okay. So let me just mention a fun thing that I'm working on now with Santosh and Pala, which is related in technique, but it's for a different problem. But there's a lot of parallels here. For the question, people are wondering, why do these language models work for next word prediction? They seem to train them only to predict the next word, and magically they generate fluent text. So it seems like outcome indistinguishability a little bit, but I wasn't here for your talk yesterday, so I'm not 100% confident in this slide. The other slides so the parallel here is, if you train a next word prediction, it seems that it looks apparently like you get text that seems kind of indistinguishable from real text that people write. So just qualitatively, I mean, and that's kind of the goal of outcome indistinguishability as well in terms of the label. There's a kind of trivial statement you can say, which is the true distribution of text fits in your family of neural networks of some size, then you should actually find the best one, and you've got the distribution. So if there's some true distribution of our text, if documents on the web are drawn from some distribution, IID, and that distribution, the next word distribution, is exactly a neural network with at most 175 billion parameters, life is good. You should find that with some amount of data, and then you really get something statistically indistinguishable. And I think that would probably have some statement like that in terms of OI as well. If your classifier, your Bayes optimal classifier happens to be, your perfect classifier happens to be in the family, then you should learn that, and it should just be indistinguishable statistically. The hard case, the interesting case, is when, of course, the real distribution is not exactly in your family. And what we show here is something, basically we're using a similar technique and then one other trick to say, okay, well, if you look at what these language models do, they complete a prefix. You give it some text and they generate, and they go on. And what we can show is that you won't be able to distinguish based on the next constant number of words, real completions from what your neural network generates. So constant number of words is good for generating stuff that looks grammatical. It's probably not good for proving theorems. And that is actually what you see with these language models. Like, they generate fluent things, they have some good ideas, but probably, at least so far, they're not generating correct proofs. And we kind of expect that you might need some more ideas. Here, I don't think you have that same limitation of the next so many words. But I do think there was like a paper that loss optimization gives you somehow some kind of indistinguishability. But I'm not an expert on that. Anyway, so that was kind of one fun thing. Another thing to mention that, I think it's relevant to this meeting is for fairness. Sometimes you do, there's tricky cases in fairness where you don't know what the groups are, right? But there's other ways to figure out what the groups could be. So here's a paper joint with several interns who are great high school students and a postdoc. And what we tried to do here is figure out what the groups are. We want to use, let's say we wanted to do an application of advertising jobs to people. Really, it's what you're saying. So, we want to advertise jobs to people, and we're worried about being biased. And what are the groups? Maybe age, maybe race, we don't know. So what we do is we take a word embedding, which is underlying still even today's huge language models, which gives you a vector for every word in the language in hundreds or thousands of dimensions. I'll show you in 2 dimensions. And you could just cluster all the words in the word embedding, and then they cluster beautifully. And then you can take one of the clusters, which will be all the names. And these are real clusters. I'm not making this up. And then you just subcluster the cluster of names, and you get these groups that pop out. And the groups you can do statistics on them, and they are meaningful. This is my family, the Israelis. My mother, the older white cluster of names, and then you have African-American names, you have younger, older, you have clusters by religion, and so on. So this gives you a way to get a handle on some kind of semantically meaningful clusters just by looking at the first names. And then you can kind of see actually the biases very clearly in the embedding. You can take the cluster of food and overlay it on top of these things, and you actually get, it just kind of spits out all these stereotypes and associations. The Israelis do eat kosher hummus and bagels and a bunch of other associations. Much more problematic is if you look at the job associations it has here. It's fine for the Israelis to have these stereotypes, but you don't want to be associated with being a jailer or a shopkeeper or stuff based on your name. And people were using these word embeddings in classification tasks where they're trying to get somebody's resume and rank them or choose a job for them. And they weren't even removing the names. But even if you do remove the names, it doesn't totally correct for problems, because often you can kind of infer somebody's gender or race or so on. So anyway, one thing that's we do that I don't want to talk about, but that is common is, you try to equate accuracy across different groups, or sometimes you even want to do affirmative action. And that's something that's not, you're not going to get with multi-calibration, because it's hard to do affirmative action if the groups are arbitrary and you don't know what the groups are. And so this gives you a way to kind of come up with groups, and then you can try to make sure accuracy is equal among the different groups.
Can I ask something about how these jobs are really, like, there's not that many supermodels, right? Like, do you have some sense about that factor?
The word embedding isn't perfect. Like, what you can do is, if you do take jobs from the Bureau of Labor Statistics and overlay them, then you get this way. These are probably jobs that we got by taking the cluster of words which were in the job cluster of words. So there's a lot of noise. I mean, supermodel is a legitimate job. I agree with you that there's not a lot of supermodels, but it may be talked about on the web a lot. So maybe a high frequency word.
Yeah. Thank you.
anyway, I mean, this is just an example. So, so basically, the high level question is when does loss,
The end.
oh, yeah, what my point, let me jump to here because this is kind of my point. This is backwards. So basically, some groups are more important than others in some applications. So in some applications, you really want to make sure, like my sister is a scientist. She hates it when she goes to a job site and they advertise to her all kinds of irrelevant administrator jobs. But maybe, you know, given that she's female, you know, and maybe given the information they have about her, that's the most accurate prediction they could make. But maybe you want to do some reweighting to make sure that no, the female scientists are being shown more jobs appropriate to them. So you're not compounding the problem. And that's this issue of compounding injustices, which is sort of that Hellman says the groups that you want to protect are groups that have been discriminated against. So according to Hellman, it may be okay to discriminate against people whose third letter of their last name is C. Like, or, you know, a fair way to choose things is somehow randomly like that. But it's at least not compounding injustices. It's unfair to the people whose last letter is not C, or third letter is not C. But if that's not a group that's been historically discriminated against, maybe it doesn't matter. So for some applications, my point is that you really you care about certain groups, and there may even be in those applications, there may even be ways of identifying groups. You can kind of get the same spirit of multi-calibration, which is, oh, I want to know what are the groups that I care about protecting, even if I don't have them identified in advance. So that's kind of similar motivation.
I think, just to say, I think the issue isn't necessarily identifying the groups. The issue is that you want to do something that's not in line.
Yes, that's right. Yeah, you want to do something in line with accuracy,
then you need to
not
think
in
about
line
it.
with accuracy, and you don't know what the groups are. So there's other ways to address this problem. Or you can think of this just as a caveat on our paper. I don't want people to think, oh, therefore, just minimize loss. You're fair. Go, you know, we've checked that box, and you know, our system is great. Well, maybe not. You know, I mean, in that application of matching people to jobs, you will have some major problems. So in applications where you are only aligned with accuracy, multi-calibration is probably more aligned with those applications. Okay, so the other conclusions from this talk are that basically, if you're a true classifier, when does loss minimization give you multi-calibration? Not always, as we saw with the half spaces, but if your Bayes optimal classifier, if your true classifier, actually, if the expected value of y given x is in your target family, great, you're done. And that was known previously. But in the case where it's not, if you can do exact loss minimization, then you get multi-calibration with respect to small neural networks. But there's actually something you can say about gradient descent and efficiency here, which is the following. So I think this is kind of neat, is usually we think about the set of classifiers, and we want to do as well as the best classifier in the family. But there could be a lot of classifiers with tons of parameters. If you turn it around, there's something called probably approximately optimal learning that we introduced with Serbi Goel, Sham Kakade, and Cyril Zhang. And the idea there is to compete with a set of the algorithms. Look at the architectures or algorithms. And there's a much smaller set of architectures or algorithms. The length of the program that you typically write to find the best neural network, the description length of the architecture, we want to compete with the best learning algorithm rather than the best classifier. There's no hope to compete with the best classifier. It's NP hard. If you want, you can think of the best learning algorithm or architecture description as constant size. So this is kind of a cheat. It's that classic enumeration Levin style thing where you say, oh, there's only so many learning algorithms. We could enumerate them all, but you could, nowadays, you don't have to enumerate them. You could run GPT-3 to search through them or do some smart architecture search, but still, it's much more reasonable to compete with them. And so then you would be comparing, you would say, okay, if I am searching if I'm doing an architecture search or a search over algorithms and I find the best one for minimizing loss, okay, then I'm multi-calibrated, not with respect to the best small neural network, but with respect to the best small algorithm that's going to find a small neural network. Does that make sense? So it's kind of an interesting take on, and so stochastic gradient descent would be an example of something that you would be searching over in your architecture search. Now, it's not a guarantee for SGD per se, it's a guarantee for small descriptions, or if you are using SGD in both your, if you're forced to use SGD in both the thing you're training the large neural network for and the thing you're searching for multi-calibration failures with respect to, then you should get that. Loss minimization will give you that kind of multi-calibration, where it's not multi-calibration with respect to all small neural networks, it's with respect to ones you would find by SGD. And that's it. So thank you very much. And I'm here, so I hope to have people educate me on all the ways that this is this is wrong, or different things that it might be missing. Thank you. I say thank you for inviting me to Simon's. I asked GPT-3 to finish the sentence, and it said, "I only wish."
Okay, great. We'll take half an hour break and meet back here at 3:30.